So before starting the talk, let me first introduce Professor Don Towsley. So he's a distinguished professor at the University of Massachusetts Amherst in the US. He's the recipient of many awards from IEEE and ACN, and among them one of the IEEE most prestigious honors, the 2007 IEEE Koji Kobayashi Computers and Communication Award. He's well known for his work on TCP. He pioneered the area of network tomography and the use of fluid models for the analysis and control of large networks in classical networking. But more recently, he became one of the leading researchers in quantum networking. And this is why I wanted to invite him to give a talk at LINX to see what researchers in the domain of classical networks can do in quantum networking. So thanks, Don, to have accepted this to give this talk at LINX on the quantum internet recent advances and challenges. And the floor is yours.
Thank you for the kind introduction. As I said to you earlier, I'm only sorry that I can't do this in person, as I really enjoy being in Paris. So what I'm going to do is really sort of give you a flavor of let's say, research challenges in quantum networks. And this really comes across from a period of years working with colleagues in the center of quantum networks that I have as a backdrop, and students. And I'm hoping that you'll find it really interesting and find the problems challenging. So why a quantum internet? Well, we all know about quantum security in the context of quantum key distribution, and it's been demonstrated, let's say, in very small areas. But really what you would like is to be able to do it, let's say, continent-wide. And that requires some kind of infrastructure for supporting it. I think you're also aware that there are now a lot of small quantum computers that have been built by companies like Google and IBM and Microsoft, and each of them individually really is not powerful enough to sort of solve an interesting problem. But again, if we had some kind of a infrastructure to connect them, then you could support distributed quantum computing and maybe be able to run Shor's algorithm and break sort of current internet security. Another application is for high resolution sensing. It's known that using quantum entanglement, you can get much higher resolution when you have very, very low signal to noise ratios. It turns out to be very useful for doing high precision clock synchronization. But all of this really requires some kind of infrastructure to sort of support the generation and distribution of quantum state. So here's the outline. I'm going to start off. I imagine that most of you are not familiar with quantum, so I'm going to do a very quick Quantum 101 overview, talk about some of the challenges, and then really draw on work that I've done in the context of routing, scheduling, control plane. You'll see a lot of analogs to what's done in the classical world, and then at the end, a summary. So let's start with this overview. We're all familiar with what a bit is. It takes one of two values, 0 and 1. There are lots of ways to sort of represent it with two-state device. A canonical example, of course, is a light bulb being on and off. But more the way that you would usually see it is some kind of a circuit where you either have a low voltage or a high voltage. And that corresponds to 0 and 1. Excuse me. In the quantum world, you have what's called a quantum bit, and you can think of this qubit. It's really sort of represented by a two-state quantum mechanical system, and there are a number of different such systems. The example that I find sort of easy to understand is photon polarization. You have your photon as a, let's say, represented as a wave, and it could be horizontal, it could be vertical. And so you could let each of those represent sort of a different state. And so a horizontally polarized, you'd say the qubit was in state 0, vertically polarized, it was in state 1. And the physicists have introduced this bracket notation. This is ket 0, but it just represents a column vector. 1, 0, 1 meaning that it's in state 0. And here, the ket 1, state 1, and it's the representation is 0, 1. What I find is when you're getting into quantum, the vocabulary is a little perplexing, but it's all sort of linear algebra. And until you feel comfortable with, let's say, the notation, you can always just translate to linear algebra. Okay, but what's interesting with quantum, let's say with this photon example, is, of course, the polarization doesn't have to be just horizontal or vertical. It could be at any angle. And so what quantum sort of introduces is this idea of a superposition of state, okay? And so here I have a ket phi, a state phi, and what it is it's a superposition of the two states 0 and 1. And it's a linear combination with these coefficients alpha and beta. Alpha and beta are complex numbers, and the square of their magnitude when summed always equals 1. So you can think of this as sort of a unit vector in sort of a complex space. Okay, and what this means is that you really have an uncountably infinite number of possible states, unlike the classical world where you just have 0 and 1. And so that brings up a question of, well, you know, how do I sort of know what the state is? How can I characterize it? And it turns out that that's not something that one can do in quantum. However, you can perform what's called a measurement. And I'm just going to give an example in the context of, let's say, this photon polarization. What I have here is a beam splitter. And so I have this photon that's in this superposition state that I pass through. And what will happen is one of two outcomes. Either it will go straight through, but in that case, it will be vertically polarized, or it'll be in the state 1, or it'll essentially sort of reflect up, in which case it'll end up in the horizontal polarization, or state 0. Okay, and that's going to happen every time you send a photon that's in this particular state. And what's interesting is that if you repeat this many times, the probability that you're going to get a photon in state 0 at the end is going to be equal to this alpha magnitude squared. And the probability that it ends up in state 1 is going to be beta magnitude squared. Okay, and each of these measurements is completely random. And the one thing that's important to understand is when you do this measurement, the photon or the qubit is no longer in this superposition state. It's going to be in one of the constituent states. I guess something, if I haven't stated it explicitly, 0 and 1 you can think of as sort of the basis for states in for a single qubit. So now I'd like to talk about entanglement, but I'll start off with, we've looked at a single qubit, but you could have 2 qubits, okay? And so they can be in a superposition state. And it turns out that they're basically represented by, let's say, 0 and 1 for each of those qubits. And so there are 4 basis states that I've listed up here. And the superposition state, let's say for state psi then, is just a linear combination of these 4 basis states. And again, if you take the coefficients, which are complex numbers, and you take their magnitudes, square them, and sum them, they sum to 1. Okay. We say that 2 qubits are entangled when you cannot describe the state of one of them independently of that of the other. And I'll say that one of the important canonical entangled states is called the Bell state, and it's given by this here. It's essentially the superposition of 2 qubits where they're in the 0,0 state and the 1,1 state. Notice the coefficient is the same for both of them. And so if you can sort of think of it, if you were to sort of measure, you get either 0,0 or 1,1 with equal probability. And it turns out this is really a very important resource for quantum communication, for sensing, and for lots of applications. And it's going to be sort of like the foundation of what I'm going to be talking about next. So we have this Bell state, and I've added these subscripts, A and B. Think of it that the first qubit belongs to Alice, the second qubit belongs to Bob. Okay, and suppose that Alice measures her qubit. Okay, and what's going to happen is it's going to yield either a 0 or a 1, and because of the way that these 2 qubits are entangled, if she measures a 0, then what's going to happen is if Bob then measures, he's always going to get a 0. Likewise, if Alice measures a 1, then when Bob eventually measures, he's always going to get a 1. Okay, so this measurement then essentially snaps it to one of those 2 states. And what's nice with this is that, 1 second, I need to get rid of something. Yeah. Well, what's nice about this is this allows Alice and Bob to share complete randomness across distances. And it's really the basis of, a lot of applications. You could see how it could be useful for, let's say, quantum key distribution, because it essentially allows Alice and Bob to generate a shared secret that's completely random, and there are ways to essentially protect it from Eve. Okay. I should mention, feel free to, to jump in with questions at any point in time. Okay, so now that's Quantum 101 for the most part. We'll be talking about a few other things, but I want to talk about possible quantum network architectures. Okay, and I want to say that there are 2 architectures that the researchers are sort of focused on. One of them, let me get rid of these okay. One of them is concerned with generating and creating and distributing these Bell pairs that I talked about. Okay, and essentially to sort of distribute them to, let's say, the Alice-Bob pairs or the applications at the edge of the network that need them. And for example, if Alice and Bob have a Bell pair, they can use it to transfer quantum information using teleportation which I will show you in a couple of slides. Okay, and basically the way it works, and I'll get into this in a little bit detail, is you have nodes that are connected, let's say by optical fiber in the network. These links create bell pairs, and then the nodes or the quantum switches essentially propagate those bell pairs to the ends. And this is considered to be sort of a near-term solution. Near-term might be 5 to 10 years of what we're likely to see as a quantum network. The second one is closer to what we know classically, and that is you would just transfer the quantum information directly. And it turns out that because of tremendous amounts of noise in the optical fibers and in the circuitry needed, let's say at the switches, this is considered to be a far-term solution. And so I'm going to be talking about the first kind of architecture. And so to motivate it, let's look at what happens if we want to generate long-distance entanglement. Okay, we have Alice, and she has, let's say, an entangled pair of qubits. It could be a bell pair. And what she decides is she wants to send one of them to Bob. Okay, and because quantum information is so fragile and delicate, it turns out that there's a good chance of it getting lost in transit. Okay, and so maybe Alice then prepares it again and tries again. And Alice prepares again, and finally, on the third attempt, she's able to get it across. Okay, it turns out that the capacity of, let's say, optical fiber of length L takes the form of e to the minus alpha L. The most important thing to take away from this is that it decays exponentially in distance. And that's not the case with classical communications. My understanding is with classical communication, it sort of decays polynomially. Okay, so how do we sort of fight this? And what has been proposed is to use quantum memories to store qubits and to introduce a repeater in the middle. Okay, and now make the job be that Alice and the repeater try to generate, let's say, entanglement or Bell states. Bob and the repeater generate entanglement or Bell state. The repeater then just, whenever something succeeds, it stores it. And then finally, when we have bell pairs on both links, what it will do is what's called an entanglement swap or a Bell state measurement to essentially splice these two bell pairs into one that span across from Alice to Bob. And I think I sort of glossed over here. What that happens then is that the capacity increases. Instead of it being e to the minus alpha L, it's now just e to the minus alpha L over 2, assuming the repeater is in the middle. And so in principle then, you could put lots of these repeaters and the capacity then will scale up. But notice it still decays exponentially in L. It's just that the decay rate is much, much smaller. Okay, now I mentioned that with an architecture like this where the network is delivering bell pairs to Alice and Bob, okay, that can be used then if Alice wants to send quantum information to Bob. Okay, and so if Alice and Bob has, let's say, end-to-end entanglement, then they can perform teleportation to send arbitrary quantum information. In the next couple of slides, I'll just sort of animate that. Okay, we have Alice over here, she has a qubit in some superposition state that she wants to propagate to Bob. And so what they do is they generate their link level bell pairs. The repeater in the middle does this Bell's state measurement, which propagates the bell pair to between Alice and Bob. And now Alice performs some local operations, essentially entangling her end of the bell pair with the quantum state that she wants to send, perform a measurement on those two qubits, which is going to generate two classical bits of information, let's say 1 and 0, and then at this point in time, Bob doesn't really know what's going on. So Alice sends that classical information to Bob. And once Bob receives it, Bob can use it to decide what kind of operations, what kind of quantum operations to perform on his qubit. And the result is that he will obtain a qubit that was in the same state as Alice. Okay, so now we have, let's say, these line of repeaters.
Do you hear me?
Yes.
I just have a question. So you illustrate the use of quantum teleportation to transfer one qubit from Alice to Bob.
Right.
Then in one of the slides before, you mentioning the long-term, one of the long-term objectives for quantum networks is to transfer directly qubits from Alice to Bob.
Right.
Is it really useful? Because with the teleportation, you do not need that.
So it turns out that it's, I guess, I'm not a hardware person, but my understanding is that it's going to be much easier to generate bell states between Alice and Bob with current technology than to just try to transfer the quantum information from Alice directly to Bob over the network. That is because you're working with sort of this known quantity, these bell pairs, there are methods for sort of making sure that they are of good enough quality that you can do this teleportation. But right now, if you wanted to send the quantum state directly, you would have to do a huge amount of quantum error correction, and the technology is just not there, and I have the sense it's going to be at least 5 or more years before that's going to be doable.
Okay, thanks.
Okay, so now we're using these repeaters, let's say, to sort of propagate link level bell pairs to the end nodes. I should mention that these bell state measurements are not, let's say, always successful. So there's some probability that it might fail, in which case then the two link level bell pairs are sort of destroyed. So let Q be the probability that it succeeds. It turns out that in generating a bell state between two nodes, not every attempt succeeds, and so there's some probability P that will be the case. So here I have an example with 4 links, and what you can think of it that what whoops, I'm not quite sure what happened. Let me share again.
It was okay, but we didn't hear you at some point.
What? I'm going to have to restart the PowerPoint.
Okay.
Okay, so now. Okay, you can see my screen, right? Okay, so we have, for each link, there's some probability P that of generating, let's say, bell pairs. Let's suppose that we have memories at the nodes that can sort of store the ends of these bell pairs. The probability that we can, let's say, propagate, let's say, these bell pairs are between 0 and 2, then are going to be, it's going to be P times Q. Q being the bell swap measurement success probability. To 3, well, you have to have 2 succeed. And to 4, you have to have 3 measurements succeed. So it sort of grows, decreases exponentially with, let's say, the number of hops that you have to traverse. I should mention, I've sort of animated this as if these measurements are being done in a particular order, but they can be executed in any order. But again, the key is you still have this exponential decay that you also had, let's say, across a single link. And the rate depends on how many repeaters you have and the swap success probability. It turns out, however, that there are other ways that you could sort of do this swapping. And one called nested entanglement swapping would look like the following. What you would do is you would do it in sort of a nested fashion. You would have, let's say, repeater 1 and repeater 3 do swaps to create bell pairs between 0, 2 and 2, 4. And then 2 would do a swap. And you can see if you had 8 repeaters, or excuse me, 9 nodes and 8 hops, you could build it up in sort of a recursive way. And so if you have a path of length n and hops, then what you get is, if you do things sequentially, as I was showing in the previous slide, you get a success probability of P times Q to the n. You have an exponential decay. But with this nested entanglement swapping, the exponent becomes log n, and you actually get a polynomial scaling in terms of the success probability. So what the takeaway from this is that the way you schedule, let's say, entanglements can affect the performance. And I've done this just for this very simple repeater chain, but you can imagine it's going to be even greater in a network setting. Okay, so let's talk about network. What we have are, let's say, a collection of quantum switches that are connected via lossy links. The switches host quantum memories, and the way it operates is the pairs of quantum memories in the switches that are connected by a link, they form bell states. And once these are formed, the switches can perform bell state measurements in order to sort of connect the bell states and propagate these bell states farther across the network. And so the concatenation of these bell state measurements and bell states then sort of allow you to get end-to-end entanglement flows, like what I'm showing. Oops. Here. So what are some of the challenges that we face then with sort of putting together a quantum network? I mentioned there are a couple of different services that it could provide. One is that it's concerned with distributing entanglement, and then it uses teleportation for transporting quantum state end to end. The other is it could be just doing direct quantum information transfer. Okay. Another set of challenges, and this is something that's close to our heart as classical networking people, is how do you do resource allocation? How are you going to share these resources across multiple users? You can see you need to have to sort of select a path over which you're going to build up this end-to-end entanglement. Switches are going to be serving different pairs of users, so you have to worry about scheduling. And we saw that exactly how you perform these Bell state measurements can affect performance. A nice set of problems in terms of performance modeling. How do you characterize the capacity region, latency, fidelity? What should the data control layer look like? Should you use classical control? How do you do measurement, management? And what I'm going to do is I'm just going to say a little bit about, first of all, I'm going to focus on a service that's concerned with distributing entanglement. I'm going to say a little bit about resource allocation, how to do switch scheduling, path selection, talk a little bit about performance modeling, and then the control plane design. Okay, so our basic ingredient is a quantum switch. It has a bunch of quantum memories where you can load, let's say, qubits, and you can read them out. You need to be able to do measurements, at least for Bell state measurements. You're going to need some quantum logic that you can apply to qubits across, let's say they're held in the quantum memories. It's useful to be able to generate qubits using multi-photon entanglement sources. And of course, combined with this is you're going to need some classical computing and communications. As we saw, if you're doing teleportation, you generate classical bits and you have to be able to communicate them. So let me talk a little bit about routing and path selection. And this is drawing on work that I did with colleagues from Arizona and MIT. And what we wanted to look at was, what rules should we use in terms of deciding what Bell state measurements to do in repeater nodes. I'm showing this for a two-dimensional grid. Probability P that we succeed in generating a Bell pair between two nodes. Think of this as a discrete time system, and so we try at each time slot to generate link level pairs. Let's say this rightmost configuration here is at one slot, the black lines indicate successful Bell states. We have Alice here in the middle and Bob here in the corner. And if we notice that if we do Bell state measurements as indicated by these dashed black lines, we have two paths between Alice and Bob. Now the Bell state measurements are probabilistic, so they may not succeed. But if they do, then we can generate one or two Bell pairs between Alice and Bob. And what we've done is look at a number of different policies. And what I'm showing is the log of the success rate between Alice and Bob as a function of the distance between them in the X and the Y directions. I'm showing three sort of surfaces. The top one is under the assumption that when we generate the link level bell pairs, that we can propagate all that information to all of the switches, so they can use that to decide what measurements to make. Okay, so the switches have global link state knowledge. That, of course, is not doable, and so we developed a heuristic algorithm that just makes use of the information from each of the neighboring switches, and what we have then is the rate decreases and more quickly than with global link state knowledge. And what I'd like to do is to contrast it with an example where, suppose all we did was we took the best chain between Alice and Bob and used that. Okay, and in that case, the rate has this behavior with a faster exponential decay. And so what we find is that it's really good to use, let's say, this path diversity to take advantage of it to increase the rate. So even with only local information, you can outperform a repeater chain, but notice you still have an exponential decay. The next slide, I'm going to skip. We've done some work on sort of sharing between pairs of Alice Bob users. What I'd like to do is to talk about the following. So the algorithms that we have generate sort of exponential decay. There's been a lot of work done on path selection, and all of them end up generating, let's say, rates between pairs of users that decay exponentially as the users grow farther and farther apart. And so it sort of raises an interesting question of whether we can actually come up with a protocol that will achieve a distance-independent rate. And it turns out by using a different kind of entangled state, you can. So here I have a switch, three neighbors, and each of them is connected to the switch with a bell pair. Okay, let's say they had succeeded. And what we do is a different kind of measurement that results in an entangled state between the three neighbors, not between, let's say, two nodes. And the state that you get is what's an example of what's called an n-partite Greenberger-Horn-Zillinger state. And you can think of it, it's just sort of an extension or generalization of a bell state, but among three or more qubits. Okay, and I'll just mention that this is used in multi-party quantum key distribution and a number of other applications, different from what I'm going to show you here. Okay, so when does this help? So suppose that we've generated our link level bell states and we have the configuration that I'm showing here. Okay, now the switches have to decide what let's say, links to perform bell states on. For example, here, does it perform between these two or these two or these two? And suppose that the switches perform them and we get the configuration I show here. Well, in this case, we're not going to generate a bell pair between Alice and Bob. Okay. On the other hand, if this switch had sort of connected these two, it would have worked out. So what happens is if you now do 3 GHZ measurements, then this switch right here will end up connecting all three of these links. Okay. Likewise, this switch will do it. And it turns out that in doing that, it creates a path to Bob, and Alice and Bob then can generate a bell pair out of that. And so what we've done is looked at a protocol, let's say what we call the 3GHZ protocol, that measures up to 3 entangled links at the switch. If it turns out that, let's say, all 4 of the links are entangled, then it just randomly selects 3 of them and measures them. You could think of it.
Did you hear me?
No, I'm sorry. Yes.
I have a question.
Okay.
Can you go back to the last slide?
Yes.
Just to better understand the GHZ states. So I understood that you can link Bob to Alice, but then if you want to have a bell pair between them, you need to have some additional operation, I suppose.
Right. Right. So what will happen in this case is you have a node here. This node will be sort of connected. Okay. This node, because it can't do any kind of a swap with any others, it will perform an operation that will essentially reduce the state that Alice and Bob share into a bell pair.
Okay.
That's what will happen. It's possible that Alice and Bob may share they may have more than one entangled qubit, and then again, they would perform a local operation to reduce it to a bell pair.
Okay, thanks.
Okay, a 4GHZ protocol would be that you measure up to all 4 entangled links. And what I'm showing here is the following. We're looking on the y-axis, it's the link success probability of generating a bell state. On the x-axis, it's the bell state measurement probability. And we're just looking at the regions where we are able, where this network will percolate. And when it percolates, we get a non-zero rate between Alice and Bob. Okay, and so this region right here corresponds to a setting where there's always a non-zero probability that no matter how far apart Alice and Bob are, they will be connected and they'll share a bell pair. This region here, which is larger, is what you get if you do 4GHZ projections. And so you get distance independence whenever you're in these regions. You have some funny behavior here that you can take care of by doing sort of some thinning. And you sort of see it in this. Now I've just got the rate as a function of the distance. These curves up here correspond, fall in the percolation region. And these curves here are outside of the percolation region. Okay, and so both of these protocols achieve distance independent rates with just one memory. You can increase capacity. I won't go through this in great detail. You can increase capacity by essentially, Alice and Bob each have 4 links. So what you do is you break up the region into 4 different spaces, and you essentially run the same protocol independently within each of those regions. And what we're seeing is that, as in the graph here, the rate as a function of link success probability for different bell state measurements. And what you can see is that you can achieve capacities that go up to 4. Okay. Okay, so let me say a little bit about scheduling. Let's look at our quantum switch. And just to remind you, the user pair, let's say that this is a switch and the end nodes are just attached directly to the switch. The user pairs generate requests for bell pairs. And again, we have sort of like a discrete time system in each slot. In the first phase, the links randomly generate bell pairs, and I'm showing them by solid lines here. In the second phase, given these outstanding requests, the switch will select bell pairs to measure. And it turns out that that's equivalent to selecting an eligible matching in a graph where we map the nodes into memories. And the outcomes of the Bell state measurement matchings then will form a set of entanglements between pairs of end nodes. Okay, and so what we've done in this setting is to, there's a lot of work on scheduling of classical switches, and so we've essentially adapted these policies to this quantum setting. And so we can characterize the maximum capacity region for a switch, let's say when there's only one memory per link or when there's an infinite number of memories per link. We've been able to show that max weight scheduling is optimal, where the weights are increasing functions of request queue lengths. And again, whether there's one memory or infinite number of memories. And of course, you get a larger capacity region, the more memories that you have. One interesting thing in this context is, suppose that there's very low demand, but your end nodes are really powerful and they have really good quality and lots of memory. Then this switch can essentially proactively generate bell pairs at the end nodes, and when a request comes for it, then it can just be served directly. And so you can achieve low to zero latency for these switches. We've also looked at quantifying the aggregate capacity of these switches. The operation is similar to what I said before. But here what we do is we use an oldest link entanglement first rule to connect pairs of users. And the workload here is that all pairs of users want entanglement. And so in the case where, let's say you have B qubits per memories per link, and link entanglement rate of mu, we've derived the capacity, which seems it's pretty intuitive. It's the rate at which you generate entanglement times the number of users times the probability that you can successfully do a Bell state measurement. And because you need two links to satisfy each request, that's the 2 in the denominator. And a similar expression for the expected memory use. And this is in the case where B is equal to infinity. What we find here, we're looking at capacity as a function of buffer size for different numbers of users. And it's very insensitive to the buffer size. If you look at the expected number of qubits that are stored, that's also very insensitive to the buffer size. And so if you have this sort of aggregate demand, memory size has little impact. Although what we find is this is in the case where the links all have similar behavior. If you have a combination of bad and good links, then you need more memory. That's what I'm saying here. Also, I haven't really said much about the quality of the memory. The assumption has been pretty much that it's good quality. If the memory is poor, then you again need more memory. And so this raises a lot of challenging problems. You know, I've talked about a switch, but we'd like to characterize the capacity of the network. We want to do resource allocation at the network level. And it raises the questions of global versus local versus no state information, or the time scale at which you would pass state information around. A lot of people think that we should be borrowing ideas from circuit switching for doing this. But I don't think I've seen much work on that. I've sort of ignored noise in the memories or noise in the gates. One of the things that this suggests, at least in the case of noise in the memories, that you may want to use a last in, first out policy to decide what, let's say, entangled pair to use. You might want to put a deadline on after which you would throw away, let's say, the quantum state because it would have degraded too much. I've mentioned that entanglement scheduling is important, but I have, so the question is, how do you include it in the network setting? I mentioned that you could store bell pairs at end nodes to be used by future requests. And so, you know, it's interesting to think that you could have some sort of overlay of storage devices where you store these bell pairs and you serve them. And perhaps you could borrow a lot from what's going on in the future power grid, where renewable sources are being coupled with energy storage devices. I just want to say one more thing, and then we're essentially done. I want to say a little bit about the control plane. And first of all, let me just say there's a bunch of work on adapting software-defined networking to accommodate quantum. But it's interesting to ask whether it might be possible to have a quantum control plane. Okay, and so we have this network here. All the nodes we'll assume are quantum processors. And the protocol, the control protocol, is just going to be a sequence of unitary operations. And what it will do is it will use a quantum walk to propagate control through the network. And I'll just say a quantum walk has two pieces to it. One is what's called a coin operation, which you can think of is selecting the next node to propagate to. But unlike a random walk, here you could do a superposition of all of the neighbors in any way that you want for propagating the control. And so gives you sort of greater power over a classical walk. And then it's followed by a shift operation, which actually propagates the control according to this selection. And I have a student who's applied this to entanglement distribution and to distributed quantum computation. Okay, to summarize then, I guess what I've wanted to point out is entanglement distribution is really very different from data transfer. And I have to say, sort of being relatively new coming into the quantum world, I'm really glad that that's what the focus is on, because if it turned out that the technology could really support direct transfer of quantum information, I think intellectually it would be much less challenging. We'd be able to borrow much, much more from classical networks. I think quantum networking introduces new problems, and it reintroduces old problems, but with sort of slightly different aspects to it. And, I'll leave you, there's a need for performance models, for doing algorithms for resource allocation, path selection, for distributing and managing entangled state in really very noisy environments. Still, I think there's an important question of what the control architecture should look like. Is it going to be a hybrid, a combination of quantum and classical, or can it be quantum, or exactly what should it look like? I didn't say anything about network management, although we're doing work on network tomography that I think would be critical to it. And so the research in this area is really in its infancy, and I think with many exciting problems. And I really would encourage classical networking people to jump in. And the thing to do, it's useful to have a quantum expert at your side. And so, for example, I'll advertise Frederic Grosshans is, if since he's in your environment, you should seek him out. Okay, and I'll stop here.
Thank you, Don. So, any question on the bridge?
I have a question.
Yeah.
It's Anastasios.
Yes, Anastasios.
Anastasios Giovannis from Sorbonne University. Thank you very much for your talk. I was wondering, you mentioned a bit the transmission of classical information in order to do the entanglement between the two nodes. And I guess this creates certain limitations to the entanglement rates that can be produced. I guess there is one part, the limitation in temporal issues on how much feedback one can get, and also, for example, when there is errors in these transmissions. Can you elaborate a bit more on this?
Yes. So it's interesting. I did gloss over it, and it turns out even when you do like these Bell state measurements to connect, let's say, local link level Bell pairs, you need to exchange classical information. First, I'll say that I think much of the work that has been done has ignored classical communication. I think sort of with the implicit assumption that somehow classical resources for classical communication are much more abundant than they are for quantum communication. And so actually, I think there's an interesting question of, you have this, let's say, optical fiber that's connecting these two nodes, and exactly how do you partition, let's say, the bandwidth between quantum and classical. Second, if you do things like teleportation, right, you do need classical information, and so with some applications, you need to know that it succeeded before you can try to do something. Other applications might be tolerant. They might allow you to use the quantum state, perhaps because they, no matter what the classical information is, they may still be able to correct later on. And so I think it's an interesting sort of problem to understand the effects for, let's say, these two kinds of applications. If you're doing something like quantum key distribution, where you have a stream of Bell pairs that you're generating, some people have said, well, you just ignore classical communication, and that just not having it increases the error rate, and you just work around that. Others have suggested that you don't have to ignore it, but you can correct for it later on when you get the information. I'm not sure if that completely answers your question, other than to say that it is an issue, and it makes some of these problems sort of very interesting when you include the effect of it.
Yes, okay, yeah, of course.
Other questions on the bridge? Question in the room? So I have two questions from my side. At some point, you were talking about multipass entanglement routing, but in the example you gave, there was only one request. Alice and Bob wanted to communicate, to share a bell pair. Maybe it was in some slides that you skipped quickly. Did you also look at the case in which you may have multi-requests at the same time, and so how to optimize the qubit throughput in the whole network?
Right. So to be honest, we paid in the work that we've done so far with respect to routing, we've sort of paid lip service to what to do to handle multiple requests. In the work that I was describing to you, the only thing that we looked at was, you have these multiple Alice-Bob pairs here, there are two, and you essentially divide the resources among them. And in the case where maybe Alice and Bob 1 are vertical and Alice and Bob 2 are vertical, the split is sort of obvious, and you would expect that you should get good performance. This example here, where they have to sort of cross paths, it turns out you can still, let's say, divide up the resources between them. And what that means is for this central node here, in some sense, Alice 2 and Bob 2 get a pair of links, and Alice 1, Bob 1 get the other pair of links. And so we've looked at things like doing time division multiplexing. We've looked at things where you sort of decide based on local information if you think that you can help one pair but not the other. And we find that you can get pretty good performance. For this nice example here, it turns out you can get essentially share. They can each get the capacity that they would have gotten if they had all of the resources. In situation here, it's not quite as good, but you can still share and get higher capacity. That's really all that we've done. I think of this as really a big open problem.
Okay, thanks. Before I ask my last question, are there other questions on the bridge? Last chance.
Yes, I have one question. I was wondering, could you, if you have several memories along a given link, have a kind of interferences?
Could you repeat your question again?
I was wondering, in the middle of your presentation, you were explaining that you could have several memories across a given link. Mm-hmm. And I was wondering if it was physically possible that there was interferences between them.
Okay, so I have to admit that I don't know enough about the technology to know exactly what might happen there. I guess talking to my colleagues at MIT, I would say that if there is interference, it's sort of minimal. It's not something that seems to have come up a lot in our discussions as something that we really have to worry about. But I know there's some quantum experts in the audience, and they might be able to say something more definitive than that.
Okay, I have another question, if I may. Suppose that you have two entangled qubits, but Alice and Bob decide to change the state of the entangle qubit simultaneously. What happens?
So I'm not quite sure what you mean by change. In the context of bell pairs, there are 4 different bell pairs. They are interchangeable in terms of what you can do with them. If they wanted to make a change, they'd have to perform local operations. What I'd have to think about whether I'm guessing that there are many changes they could do where they wouldn't have to pass any information to each other, but there might be some changes where they'd have to sort of coordinate classically, maybe requiring a correction. Something related to what you said is there's been a lot of work on that you might have, let's say, lots of users and they share a multipartite entangled state. And there's a lot of work focused on what kind of transformations can be made on that state where people don't have to exchange information, what transformations would require coordination, what kinds of, let's say, if you wanted to break this multi-party state down to just a bunch of bell states among pairs of users, what's possible without any kind of coordination, what requires coordination. I'll just say that that's sort of like a highly researched topic these days.
Okay, thank you.
I see Anastasios as a question.
Yes, so you have discussed the role of local and global information availability and how this affects routing and scheduling. Apart from the plot that you have shown, are there more like deeper studies about this? And also, based on realistic systems, how much information can a node have to performance scheduling? Can we actually assume that a node can gather all the information?
I mean, that's a very good question. So I wouldn't say there have been deeper studies, but for example, here's some work that has come out of actually collaboration with a group at the University of Arizona. Suppose that you can store these link level bell pairs in memory for a while. Then there's a PhD student at Arizona has looked at a time multiplexed version of this, where you have, let's say, a frame that consists of k slots. You generate as many link level bell pairs as you can during those k slots. And at the same time, because the k slot is much longer in time, it allows you to collect state information from other nodes. And so she's looked at what you might be able to do in that case. And what she finds is that you can get close to the sort of the surface I show you for global link state knowledge. And papers on archive, and if you send me an email, I can send you a pointer to it. Otherwise, I think all of the work that has been done has been heuristic in that, trying to borrow some ideas from classical network and come up with sort of heuristic path selection and routing algorithms. I think there's a lot of room for a really principled study in this realm. Oh, and this other work though does, like, they take sort of like irregular topologies. They don't use 2D lattices like we have.
Okay, I would be interested in that. Okay.
Send me an email and I'll send you some pointers.
Okay, thank you.
Other questions? So I will ask my last one. It's maybe a bit more personal. Before you were working on classical networks, and I just wonder why make you change to switch to quantum networks?
Okay, so I work closely with a colleague, Saikat Gua, at University of Arizona, and I met him, I think now it's about 15 years ago. He graduated with a PhD in sort of like quantum photonics and quantum information theory from MIT, joined BBN, and they didn't have enough money for him to just work exclusively on quantum. And so we ended up in a project on classical networks, and I think we ended up having a lot of respect for each other's work. And for years, he kept telling me about all these interesting, exciting problems in quantum. And after maybe 10 years, I really got hooked and got into it. And so again, I would encourage you, if you want to do something sort of meaningful, you should connect with somebody who's in quantum. And as I said, you have local resources, you have quantum researchers who are interested in networking, in network science that you can draw on. And let me just say, there is a learning curve, but I think it's worth it, especially if you're young. You know, all I can say is I wish I were 15 years younger.
Okay, thanks again, Don.